So far in this chapter, we've discussed three different tools: mathematical or weak induction, strong induction, and the well-ordering principle. If these things seem to have a lot in common, that wasn't a coincidence. They are, in fact, equivalent to each other. In other words, anything you can do with one, you can also do with the other, although possibly not as easily. So to prove this, we would have to show three things: that one of the methods implies the second implies a third, and the third circles back around and implies the first. Now, which ones are used to prove which other ones isn't important, as long as we eventually do this complete round robin kind of circle. Now, showing all three is really more theoretical detail than we need at this level, but I will show one of the three just so you can get an idea of how this kind of proof works. So what I want to show here is that strong mathematical induction implies the well-ordering property. In other words, if we assume that strong mathematical induction is valid, that it works, then every subset of the positive natural numbers has to have a lower bound. Because remember, that's what the well-ordering property says. So here's how we're going to do this. We're going to do this by contradiction, right? So let S be a non-empty subset of the natural numbers. All right, so what we need to show is that S has a minimal element, and we're going to do that by contradiction. So assume S has no minimal element. Then I'm going to define this proposition. Let P of n be the proposition n is not an element of S. What I'm going to do, just kind of looking ahead, I'm going to show that this is true for every natural number, right? And doing that is going to show that there are no elements of S, right? That S has no elements in it, and that's going to contradict the assumption that it was non-empty. So I'm going to do this using mathematical induction, right? So our basis step is looking at 0. So if if n equals 0, then P of 0 is true, because if 0 was an element of S, then it would be its minimal element. Right? 0 is the smallest positive natural number. So if 0 were in there, that would have to be the minimum. Since our set doesn't have a minimum, 0 can't be in there. Right? So P of 0 is true. All right, now remember, we're using strong induction here, right? So strong induction says assume that P of K is true for all integers between 0, I got to put a variable in there, don't I? All integers m between 0 and k. In other words, let's actually write this. In other words, none of the numbers from 0 to k are in S. In other words, for all, let's write this out, for all j in 0 up to k, right, j is not an element of S. That's our strong induction hypothesis. Now, if k plus 1 is an element of S, then k plus 1 would have to be its minimal element. Because all the smaller numbers up here, all the smaller numbers have already been included. But S doesn't have a minimal element. But since S has no such element, K plus 1 is not an element of S. So this means that strong induction implies that for all, strong induction implies that P of N holds for all natural numbers N, which implies S is empty. Don't put a period there. S is empty, which is a contradiction. Right? And since we've reached a contradiction, our original assumption that S has no minimal element must be false. Right? Therefore, S has a minimal element, which is what we needed to show. So this brings us to the end of our discussion of strong induction and weak induction and the well-ordering principle. We are going to continue to use them from time to time, and we do have more forms of induction to talk about. But to do that, we're going to have to talk about another tool first, something that is related both to sequences and to computer science, software development in particular, and that's something called recursion.